Hello and welcome to this clip going through question 3 and 5 from the Rings Polymers and Analysis paper F324 from June 2016. So obviously in question 3 it says in the first sentence that we're looking at peptides and alpha amino acids. So it might be worth remembering what an alpha amino acid is. So it's basically a central carbon with an amine group on one side, carboxylic acid group in the other, an R group and an H coming off that. So the first thing to think about is what actually changes. So the carbon double bond oxygen going to C single bond O means that the oxygen has to pick up a pair of electrons. That must mean the pi bond breaks. But in order for this to happen, the OH minus ion must be attracted to the delta plus carbon in the first place. So I've moved my delta plus slightly out of the way so you can put the curly arrow from OH minus to the delta positive carbon. So each of those two adjustments would give you a mark. So we can now move the page down a bit and look at the next part, which says the tripeptide is hydrolyzed and the resulting mixture containing 3 amino acids is neutralized, and a student tries to separate and identify the 3 amino acids in the mixture using thin layer chromatography, or TLC. And the diagram shows the apparatus for the experiment and the chromatogram produced. So if we move the page down a little bit, we can start to put in some of the answers. I'm just going to move the page all the way down so we can see that it's 3 marks. Okay, so it asks you to suggest why there's only 2 spots. So you measure 2 distances. One is the distance moved by the spot, which is x, and the distance moved by the solvent, which is y. So to calculate the RF value, you divide the distance moved by the spot over the distance moved by the solvent and compare to data books or known values. So if we now move the page down a bit, and then we have a bit of space to say why there's only 2 spots. So the reason we're looking at that is that 2 out of the 3 amino acids will have similar structures to each other, and therefore the intermolecular forces will be quite similar, so that would lead to similar absorption to the mobile phase, so they'll travel up together rather than separate out. So we now need to move on to the next page. So the 3 amino acids are in the tripeptide are given in the table. Now it's worth pointing out that when it says isoelectric point, that's no longer on the new OCR spec. So I will do it anyway, just to illustrate what they're talking about, but you don't need to worry about this for your exam. So basically what happens is the pH at which the amino acid exists as a Zwitterion. So it's NH3 plus, sorry, it's NH2s turn into NH3 pluses because they picked up a proton, and the COO minuses turn into COO minus, sorry, the COOHs turn into COO minus because they've lost a proton. So the structure of aspartic acid when it's dissolved in a high pH solution. So what's happening is that the COOH groups will both have lost a proton, and they'll be behaving as acids. So if you look at aspartic acid, you'll see that the R group, remember from the previous part of the question, the R group comes off the central carbon. The R group is also containing a COOH. So both of those will have lost their proton in the presence of a basic solution. So moving the page down to be able to draw in that structure. You'd have something like that. Now then they want a structure for the tripeptide. So what I've got to do here is take the information from the top of the page and pop it down here so you can see it. So the tripeptide will have each of the amino acids in it. So just to help you visualize it, I've labelled each part of the tripeptide according to which amino acid it comes from, and what we have to do now is to put in the chiral carbons. So that takes us to the end of this first question. Let's now move on to question number 5. So this is obviously a spectroscopy question, looking at NMR and mass spectroscopy. So we have to think about 2-aminopropan-1-ol, but perhaps in its displayed form, so you can see all the environments. So we need to remember that it's also dissolved in D2O. So that means that there's no OH or NH singlets, so the two highlighted functional groups don't turn up. So obviously that's what was on the mark scheme. Let's now have a look at why that might be. So in the first filled out row of the table where it says 0.8 to 2.0, the relative peak area is because there's 3 hydrogens in that particular environment and there's 1 hydrogen being picked up in the adjacent environment. So in the next one along, it's a relative peak area of 1 because there's 1 hydrogen in this environment, but there's 2 non-equivalent hydrogen environments adjacent. Either side, there's a CH3 one side and a CH2 OH, or just a CH2 in this case, because of the D2O on the other side. So in the third case, there's 1 hydrogen environment adjacent, so it's a doublet, N+1 rule, and there's 2 hydrogens in this environment, so it becomes a doublet, the peak itself. So let's now move the page down a bit. Now here we've got the mass spectrum. I'm going to move the page down further to see if there's anything written underneath that. No, so we're going to need to take this bit onto the next page of the clip. So this time they want the formulae for the fragments that give peak 1 and peak 2. So the way to do this is to think about what fragments might add up to 75 for peak 1 and 44 for peak 2. Now peak 1 is quite straightforward because it's obviously the molecular ion, and the fragment at peak 2, you need to take a section off that until it gets down to 44. So if you break off the CH2OH part, that leaves you with CH3CH and H2+. So the next part of the question wants the reagent and conditions for the synthesis of 2-aminopropan-1-ol from 2-chloropropan-1-ol. So what's happening is an amine group is replacing a Cl. So you need ammonia dissolved in ethanol to make this one work. So moving the page down to make some space, it says the sample prepared by the teacher from 2-chloropropan-1-ol is not pure. And it also contains compound D. And compound D has a molecular formula of C6H15NO2. So you need to suggest the structure of compound D. So if you recall, you can sometimes get further substitutions on the amine group. So you could get the chloro alkane actually coming back, and another molecule of it coming back and attacking again. So what's happened is the haloalkane has actually substituted once more onto the same amine group. So this next part is about compound E. So there's 2 functional groups, or actually there's 3. There's a phenol, obviously, and then there's an amide, and then there's an alcohol. So they need to be put into your answer as well. So moving the page down, they want the 2 organic products formed when compound E is heated under reflux with dilute hydrochloric acid. So essentially the amide is hydrolyzed and the compound splits. So what you get is a carboxylic acid and an ammonium ion. So that takes us to the end of this clip. Hopefully it's been fairly useful, and it's certainly gone through quite a bit about the organic that you covered over the 2 years. So as always, thanks for listening, and until next time, see you soon.